Treja, 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 treja. There you go. Okay, so look at bonds a couple different ways today. Actually, one of the most powerful ways of talking about a bond is to talk about the energy in a bond. Okay. Now, the energy we talk about in a bond is called the bond dissociation energy. So, dissociation. Association means to put things together, right? So dissociation would be to tear them apart. So it's the energy to tear apart a bond. The energy you have to put in to break a bond. Because remember, a bond is supposedly giving us low energy. So to get it apart, I'd have to raise that energy. So making the bond is low energy, tearing apart is high energy. You got to put energy in to tear things apart. Okay? Of course, it's kind of logical that double bonds have larger bond dissociation energies than single bonds. If it takes energy to take apart a bond, it makes sense it would take more energy to tear apart two bonds. It's called a double bond, but it's not quite twice the energy. It's a little short of twice as much. But it's significantly more. And of course, triple, tearing apart three bonds has got to be harder. Just to give you a sense of scale, to break a single bond between two carbons takes 347 kilojoules per mole. Okay, so you're going to break a bunch of them. You're never going to break one at a time, but 340. Well, technically you are breaking one at a time, but you're not going to be able to count it. So 347 kilojoules for each mole to tear two carbons apart. If you make it a double bond, it's almost twice as much. Twice as much would be right at 700 kilojoules. 657, almost twice as much. And the triple bond is almost three times as much. Another 300 up. And every kind of atom bond has its own bond dissociation energy. Sorry. So the larger the bond energy, the harder it is to break. So large bond energies make chemicals less reactive. If you got to get out of a hole before you go anywhere, the deeper the hole, the harder is it going to be for you to go anywhere. So the triple has got more energy, so it's more stable. One of the places that shows up is in our atmosphere. Okay, two components of our atmosphere, O2 and N2. O2 is double bonded, and N2 is triple bonded. And one of the big challenges is to take the nitrogen in the air and find a way to get it into proteins. Because proteins all have nitrogen in them. And the amino acids means it's got to have the N part. And that's hard for living things to do. There's a limited set of plants that can do it. And they're called nitrogen fixers. So you'll find that they have the nitrogen in the soil gets turned into the proteins in the plant. So somehow you got to get that nitrogen in the air into the soil. You got to get it to react. So you'll find that farmers rotate their crops. They'll grow a crop of corn, and corn uses up all the nitrogen in the soil. And then the next year they'll plant soybeans. Soybeans, while they're growing the soybeans, also can actually fix the nitrogen. So they put some nitrogen back in the soil. So if they alternate crops, because if you try to grow corn the second time, there wouldn't be enough nitrogen unless you use fertilizer. So up until the early 1900s, the only real fertilizer they found was off of islands where birds had been pooping for hundreds of thousands of years. And the poop was hundreds of feet deep. And you would mine that, it would be the only source of fertilizer around until they figured out a way to fix nitrogen, a chemical process, and made artificial fertilizers. And it's brought up something called the Green Revolution because suddenly everybody can fertilize. Also, the same nitrogen compounds that go into fertilizer go into explosives. So it also made World War I possible because it made all the explosives they needed possible because that involves fixing nitrogen too. Yeah. But fixing nitrogen is tough because you got to break the triple bond, and very few things can do it. We can't do it. Okay. Another way, the difference is that single bonds are longer than double, and triple bonds are even shorter than double. We had said that earlier as our evidence of resonance structures, that the resonance structures really had 1.5 bonds. And we could tell because it was in between length of a full bond and a double bond, a single bond and a double bond. So just looking at the energy it takes to tear those bonds apart tells you a lot about how they're going to react. Okay, so we spend a whole group of time on atomic orbitals. The orbitals where you have a chance of finding them in an atom. But when you put the atoms together and make a compound, when you make a molecule, the orbitals have to change. Okay? How do I know the orbitals have to change? Well, think about the orbitals you have to work with. S's are spheres, right? So they can be any direction. But P's are lobes at 90 degrees from each other. How does that explain any of our angles? Might possibly be able to get away with the 180, but it's not going to explain the 120. Right? It's not going to explain the 109.5. Okay? So one way of looking at the electrons and bonds is to talk about how the orbitals change when you make a molecule. They no longer, the atomic orbitals are going to have to turn into molecular orbitals. The electrons are going to belong to the whole molecule. That electron belongs to both atoms. So it belongs to the whole molecule. Okay? And the way you make it, you're making a molecular orbital, is you overlap atomic orbitals. You overlap the atomic orbitals from one atom to the next. Those molecular orbitals are where the electrons are going to be found in the bonds. So we're talking about where you have a chance of finding the electrons that are in the bond. So just like the other orbitals, it's room for two. And there are two types of molecular orbitals. And knowing our love of the Greek alphabet, they're named after Greek letters. Okay. The first type is called a sigma bond. The Greek letter, lowercase sigma, looks like an O with a tail in the front. It eventually became RS because people went tail first and then got lazy and didn't bring the tail all the way up, and eventually turned into our lowercase s. But circle the tail on top, sigma. And that's between the atoms, it's between the atoms, let's put it between the atoms' nuclei. So right between the two nuclei. The second kind It's called a pi bond, a pi orbital. And that's going to be above and below the atom's nuclei. Okay, so we got two types, sigma and pi. We'll talk about how they form. So, sigma. A sigma bonding orbital. Okay? It's an orbital that's in the bond. So we call it either a sigma bond or a sigma orbital. The two are interchangeable. It's called sigma because it's the only thing s orbitals can do. So they named it after the letter S. Okay? So I start off with two s orbitals, one on each atom. Ooh, what the heck happened there? Okay. So I start off with two s orbitals. They're separated. When I push the two atoms together, they start to overlap. And when they start to overlap, then the orbital changes shape. And those two electrons can be found on either of those, around either of those two nuclei. Oops. So I take my s orbitals, push them together. Once they overlap, they change shape. And you'll notice that there is a good chance of finding the electrons between the two nuclei. That spot in there, it's a good chance of finding it. Sigma happens right along that axis. It makes sense that that's what would have to happen. We'd have to have one orbital that both atoms could hang on to. So the orbital belongs to the whole molecule now. Now, s orbitals can do sigma bonding, and that's all they can do. P orbitals can also do sigma bonding. Remember the p orbital looks like, they say, a barbell? Okay, got the two lobes on each end. So I take the p orbital on one atom, p orbital on another atom, and push them together. Look at where they're going to run into each other. If I push them together, they're going to run into each other right between the two nuclei. Okay? They're going to overlap there. And again, there's a good chance of finding the electrons between the nuclei. It goes right along that axis. So you take the two p's, push them together, orbitals change. So happens along the axis. And that's two ways you can make a bond overlapping in between. This is how all bonding starts. You put two atoms together, the first thing that's going to happen is their s orbitals are going to overlap or their p orbitals are going to overlap. Okay? So two ways to make a sigma bond, one from the s's, one from the p's. Pi bonding uses the p orbitals on separate atoms too, but it picks the two that are parallel to each other. Because we already talked about these. The ones that are lined up with each other are going to overlap down the middle. The ones that are parallel with each other ones that are parallel each other, will run into each other above and below. And they'll overlap. That's where they're going to overlap. They're going to overlap at the top and the bottom. And notice there's no chance of the electron being found there. The electron's going to be found above and below. And that's why you can make a double bond. Because the first one puts the two electrons in the middle. The second one puts the electrons above and below. So a sigma happens, so that's how you get to a double bond, is you have a sigma in between and a pi above and below. And what that's going to do to your molecule, okay, where is it? There it is. Tinker Toys for Teachers. Okay. So you're going to make a double bond. You're going to bring these two atoms together, and the sigma is going to happen in between. We can represent the sigma with a stick in between the two. And the pi, oops, is going to happen, apparently just got ruined, but above and below. So my hands are where I have a chance of finding up to 2 electrons, and the stick is where I have a chance of finding up to 2 electrons. Okay? Notice what that does to the molecule. It makes it flat. That's really trigonal planars. Another reason why the trigonal planars are flat is because they got electrons above and below pushing them towards each other. Does that make sense? Okay. So things with double bonds are flat, trigonal planar, because they make a pi bond that keeps them flat. Is that right? Whoops. Okay. So all single bonds are sigma bonds. The first thing that's going to happen when you put two atoms together is they're going to overlap each other. In a double bond, it's going to be a sigma and a pi. The first bond's the sigma, the second bond's the pi. Okay, so that leaves us with the triple bond. Okay. So if I take two atoms, and first I make a single bond between them, then I'll be able to make the double bond between them, right? There's only one place left for the electrons to go, and that's because I haven't used the p orbitals going sideways yet, right? So I got the p orbitals here that I haven't used. And here, so that I can make a total of 3 bonds. I can make the sigma down the middle, the first pi top and bottom, and the second pi left and right, front and back, however you want to look at it. Right? I got room to make another pi bond there, right? Everybody see that? And that's why I can get a triple bond. It's why I can't get a quadruple bond. I can't get a quadruple bond because there's no more place I can put electrons. If I've got the top and bottom, left and right, and middle all filled in, there's nowhere in here that you can put another electron. It's not going to get pushed out. So that's how you can get 6 electrons between 2 atoms, because only 2 of them are actually between the atoms. 2 of them are above and below, to them front and back. And notice what that force is here. That I have to get a line. If I have a triple bond, I have to get a line because I can't go up and down because there's electrons there. I can't go front and back because there's electrons there. Everything's going to get pushed into a line. So with the triple bond, we said we made it linear on our blue table yesterday, right? Okay? Gotta be careful. I tend to break these, so. And they don't make them anymore. Okay, so that's what's going on. That's why it has to be. That's why the bonds have to get shorter. You got to be closer together before you can, you can overlap like this, and even closer together if you want to make that third one. So single bond, because if you think about it, it doesn't make sense. The more electrons you put in there, the closer they get together, electrons repel. But no, they got to get closer together so they can overlap and change where they're found. So right? Okay. So that's why we get linear molecules. So, makes sense? So on our blue tables, we got a column we can fill out. We left one blank, didn't we? So, the first one. Sorry, fighting a nasty cold. Okay, types of bonds. We said, for the first one, we said the types of bonds were all single. So, any pi bonds? No, so it has 0 pi bonds. The next one we said, the 3 and 1. Those were all singles, right? Any pi bonds? No. And the third one, 2 and 2, all singles. Any pi bonds? No. Okay. 3 atoms, no lone pair. We said that there had to be, the only way that's going to work is if you have a double bond in there someplace. So you're going to have 1 pi bond because the double bond, the second bond is a pi. Same is true for the next one, right? 2 atoms, 1 lone pair. You've got to have a double bond, or the center atom's not going to get that octet rule. Okay? And on the last one, we said in order for that to work, you either had to make 2 doubles or a triple. In either case, you make 2 pi bonds. Okay with that? So we've explained flat and line, right? So tomorrow we'll deal with 120 and 109.5. Okay, but molecular orbitals explain flat and lines. Right with that? Okay, that's what I got today. Way to get good at this stuff is to yell at your neighbor, copy fast. No. Practice. You're welcome. So you're going to draw some structures and then tell me about the shape of those pieces and the bond angles and sigma and pi bonds. Okay.